SwayamPrabha. Digital India. Educated India.
I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. The title of this lecture is Deep Meta Learning, that is learning to learn for task offloading in edge cloud systems. Preface: in this lecture, we shall discuss meta learning methods applied in the context of task offloading in dynamically changing mobile edge computing environment or the edge cloud system. So, the meta reinforcement learning based offloading algorithms that use deep Q learning with first order meta learning we will cover in this part of the discussion. Now, let us understand here a bit about why these meta learning methods are important. Now, here we have, let us say that the mobile devices or IoT devices, which are large in number and often they are generating the huge amount of data. Now, this particular data requires computation, whether the computation are to be done on the device or it is to be done in the edge cloud system. This is an edge. So, whether the computation is to be done on device or on the edge or on the cloud. Now, there are two sides that this edge and cloud is experiencing a common fluctuating or dynamic scenario. Dynamic scenario means that node membership and the load variations are some of the aspects of dynamic interventions, and also the outages, network outages. So, this will become quite dynamic scenario and also the data which is coming from here. Now, the thing is, so how are we going to understand or train the model for task offloading? Task offloading methods, which are often the reinforcement learning based learning, often assumes that these particular scenarios are static in the form of edge cloud system. If they are static, then this particular deep Q learning or DQN is a good solution for decision making in the task offloading scenarios. How about if the situation is dynamic and this is not going to capture this side of this particular environment. So, if this environment is not captured, then you know that the agent which decides about the task offloading may not get the accurate viewpoint, and the task offloading often will experience a low performance in that case. So, we are going to see that what is the method of capturing this dynamic situation, and therefore, we require a concept of a meta learning to be involved here in the task offloading system. So, meta learning is to learn about what are the things we have learned. So, for example, we have learned about the changes, and whenever a new load comes for the task allocation, then it has to now adopt with these kind of learning, and therefore, this meta learning is the ability learning to learn quickly, that means adaptively it will be able to learn without further training. That means, the training time and the training data set becomes a bottleneck in the traditional system. So, with that into an effect, we are going to use this particular meta learning, and we will see that in the edge computing this meta learning is going to be a major development. So, let us introduce this entire environment. So, in a distributed computing paradigm, this edge offloading that migrates the complex task from IoT devices to the edge cloud server can break through the resource limitation of IoT devices, reduce the computing burden, and improve the efficiency of the task processing. Usually, the deep reinforcement learning based task offloading and the resource allocation methods fail to adopt the changing environment, such as dynamic edge cloud environment that we have already explained. So, for example, with the rapidly changing IoT scenario, readjusting the task offloading decision and wireless resource allocation every time this machine, this mobile edge computing environment changes, causes a higher service delay and incurred cost. So, this particular situation, which is called dynamic situation, and the training time requires lot of data, and the time often not able to handle this dynamic MEC environment with the traditional DQ learning based offloading tasks. So, therefore, DRL based decision making model like those deep Q learning, PDQN, DDPG will fail to make accurate task offloading decisions, because of the training or a retraining requires a large data set and the training time to adapt to the dynamic environment. So, this model would require retraining from the scratch, which makes the learning the efficiency very slow. Such repeated training will consume the resources and weaken the performance of MEC system. So, here the deep meta learning methods come into the play to handle the problem of poor neural network portability. So, the meta learning methods ensure that the offloading decision model can quickly adapt to the new environment by learning the proper initial parameters of the neural network, also called as meta parameters. Now, such initialization method is called meta initialization method. Means with the proper parameters of neural network. Now, meta learning is applied to learn the initial parameters of the neural network, that is deep Q network, under changing MEC environment conditions, so that the offloading decision model can quickly adapt to the new and the previous and the possibly previously unseen environment. So, here we are going to see how meta learning is applied to learn the initial parameters of the neural network, that is deep Q network, under changing MEC condition, so that the offloading decisions can quickly adapt to the new and possibly previously unseen environment. So, the goal of meta learning is learning to learn fast, that is to make the model becoming a learner. So, after completing the multiple learning tasks, the decision models can quickly complete the new learning task by learning prior knowledge or exploring the learning strategies. Therefore, it quickly adapts to the complex and changing environments and can be used to improve the robustness of task offloading decisions in IoT environment. Now, let us see about more details about the meta learning. So, meta learning is a process of learning how to learn. So, meta learning algorithms takes in a distribution of tasks, where each task is a learning problem and it produces a quick learner. So, a learner that can generalize from a small number of examples. So, one studied meta learning problem is few shot classification, where each task is classification problem, where the learner only sees a few input output examples from each class, and then it must classify new and possibly unseen inputs. So, here you can see in this example there are three different type of learning samples or learning models using training data. There are three different type of training data, and let us see that if let us say a new input comes, how which model is going to be very close to it, which is being adopted in the fast changing modes. So, for example, there are three different training data, and here when a new input comes, you know that this particular input is quite close to the trained model, which is having 99.5% accuracy. If you compare it, is the distance between these two models. So, therefore, it will adopt to pick at that point this particular model, which is already trained. How about other models? So, this model has only the correlation of only 0.4% probability. Here it is 99.5% probability. This particular model is closed when a new input of this type is seen. So, we will see it more detail in this particular method, and this is called the first order meta learning. So, this algorithm, which is called first order meta learning, called reptile algorithm, seeks an initialization of parameters of the neural network, such that the network can be fine tuned with a small amount of data from the new task. Now, reptile or simply performs stochastic gradient descent on each task in a standard way, and it does not unroll the computation graph or calculate any second derivatives. So, this particular algorithm works by repeatedly sampling a task, training on it, and moving the initialization towards the trained weights on that particular task. Since there is no second order derivative calculation is needed, it is called first order meta learning algorithm. It takes less computation and memory, and that than second order meta learning models, that is model agnostic meta learning ML methods. Let us see this particular method, that is first order meta learning algorithm, in great details. So, this first order meta learning learns an initialization for the parameter of a neural network, such that when we optimize these parameter at the test time, the learning is fast. That is, the model generalizes from a small number of examples from the test tasks. So, this particular first order meta learning is given as follows. So, here you can see that it will go on initializing with a phi the initial parameters, and then it will go on this particular iteration to update it. Here can see that there is a sample of a task, and corresponding to a loss function on the weight vectors, and then compute this update function denoting the k steps of gradient descent method or Adam optimizer. It will update this particular gradients and update this particular initialized or initialization parameters. Let us see this complete overview through this particular example. Now, let us see that through meta learning it tries to learn the parameters up to this point. Now, at this point there are 3 different trained models parameters. Now, at this point it will see that this particular meta learning model where at that point it is close to. So, if it is close to, let us say theta 3 star, then this particular model will be shifted to this particular trained model. Otherwise, if it is this particular theta 2, then it will shift to the theta 2, theta 1, then it will shift to the theta 1. So, it depends upon the meta learning which of the trained models, that is it is going to be useful in the dynamic changing scenarios. So, first order meta learning in the task offloading, that in the dynamic edge cloud system, the system resources such as network bandwidth, execution capacity of the remote devices are subjected to the dynamic changes over the time. So, such changes may cause performance of the trained decision making model to become inaccurate and causing the incorrect offloading decisions, which may lead to the network congestion and resource over underutilization. Now, meta learning algorithms aims to find the optimal meta parameter theta for a decision making model that can adapt to a new MEC environment in a fewer number of learning steps. Such a meta learning setup is often called as a few shot learning problem. Now, we will discuss the deep meta Q learning based task offloading, that is MDMQTO algorithm, which combines the concept of the first order meta learning with the deep Q learning approach for making the offloading decisions model adapt quickly to the changing MEC environment. Now, DMQTO implies the deep Q learning method, which gives the better sample efficiency as well as has the advantage of off policy learning for better exploration. Now, let us see about the first order meta learning applied to the task offloading problem. So, this algorithm we call it as DMQTO algorithm, which consists of 2 phases. The first is called task learning phase and the meta learning phase. So, task learning phase represents the inner loop of the meta algorithm, and in this phase the DRL agent is trained using trajectories and episodes from the random MEC environment. So, meta learning phase represents the outer loop of meta algorithm. So, meta learning phase represents the outer loop of the meta algorithm. This phase, in this phase the set of parameters B learned previously in the task learning phase is used to update the meta parameters. We want this meta parameter theta to be as close as possible to all these learned parameters. To be as close as possible, as close to all the learned parameters, so that it takes less number of learning steps for the meta parameter to converge to the new parameters. In the other words, we directly minimize the mean square error between the meta parameters and the learned parameters, that is the theta and theta star. Let us say this is theta star 1, this is theta star 2. So, this is called the meta parameter and this is called the learned parameters. So, this particular algorithm, you can see that this is the learning phase and this is the meta learning phase, this is the outer loop. Now, let us consider the system model. In the system model, in the edge cloud network consists of multiple clouds, here you can see, and the edge servers interconnected via the network and the IoT devices. Devices directly connecting to the nearby high bandwidth edge servers. Now, the environment is designed to model the multi-user edge cloud scenario like MEC. So, it is based on an underlying edge cloud network topology where each server or the device is referred to as offloading location. So, there are three different. So, offloading process optimizes the offloading decision based on two metrics, the task execution time and the energy consumption, and takes into consideration the environment parameters such as available bandwidth, transmission delays in the network, computation, power of the edge, cloud servers and energy requirement of the user and the edge servers. Now, let us see about the application model. So, the IoT or the mobile application have the respective component dependency graph CDG, which is nothing but a directed acyclic graph. You can see that these are different applications which are running in your mobile phone, and together it will form a graph which is called a component dependency graph. CDG, and it often represents the application model. So, the CDG is nothing but a DAG, directed acyclic graph. So, the nodes here represent the tasks. In a while, the edges represents the data dependencies, that is the communication between data dependencies. That is the communication required between the tasks. So, after the execution of a certain task, the output will be produced and has to be moved to the network to the location where the next task is placed. For example, if it is placed on an edge node 1 and if this is placed on edge node 2, then after this completion of this particular task, the output will be communicated to the next task, which will become the input and then only it can start the execution. So, this is having the data dependency and this data dependency which is captured in the component dependency graph. So, this example DAG is for gesture recognition application shown in this particular graph. Now, let us consider the system model after having understood the application model. In order to leverage the computation resources of the edge servers, the application would require to offload its workload according to the multiple dependent tasks and across the available remote locations using an appropriate offloading scheme. Such a scheme should be able to produce the offloading solutions of the form P, which represents the sequence of n offloading locations. So, here you can see location 1, location 2 and so on of location 1, where Li represents the task offloading locations. So, here you can see that these are all application tasks which we have seen in the form of component dependency graph nodes are shown over here. So, that means these nodes are now overlaid or mapped or offloaded into these particular locations. So, this is having the location 4, that means it is offloaded to the cloud, and this is offloaded again to the cloud, and one is offloaded to the edge, and this is also offloaded to the edge. Similarly, this 0 is also offloaded to the device, that is IoT device. So, here you can see that there is a communication link and here there is a data dependency. Red means data dependency, that means here this is captured as a data dependency, and otherwise this is a communication link. So, having understood the system model, let us go and formulate the Markov decision process formulation. So, in MDP it consists of the states. So, the state consists of the features as task embedding for CFG, DAG and partial offloading locations. So, this comprises of the states. So, states comprises of the number of tasks which are, let us say that here in the component dependency graph these tasks are represented. So, here all these particular tasks will become edge, that is the number of tasks will come from the component dependency graph. Now, similarly W is the task embedding. So, task embedding represents the locations of these different tasks to be assigned in these nodes, and P is the partial offloading solutions. So, the task offloading, task embedding can be used to convert the component graph of the application to the feature space. So, this is called a feature space. So, example over here, let us say V0, V1, V2, V3, V4, V5, V6, V7. So, V0, V1, V2, V3, V4, V5, V6, V7, and these are all having this partial offloading. So, partial offloading P1, P2, P3, P4, P5, P6 is shown over here, and you know that the output, that is the edges, the dependencies are also captured over here. So, D out is equal to dependencies are measured over here, D01 is this particular dependency, all these dependencies are mentioned over here in this feature space. So, feature space has now representation of this component dependency graph and DAG, and this represents the state. This entire scenario represents the state in the MDP formulation. Now, let us see about the action, the second part of MDP formulation, that is called the actions. So, actions includes the locations where the tasks are to be loaded, which can be either one the locations at the edge nodes or the locations the cloud node. So, there are 3 different locations are possible to the where tasks to be offloaded. Three locations. The first one is called IoT device. Let us say it is having the location 0. Second is the edge node. Let us say it is the location 1. Third is the cloud. Let us say that it is having the location third one. So, the first one is called IoT. The second action is up to this point, the edge nodes, and third one is about the cloud. So, that becomes the action, means the actions include the locations where the tasks are to be offloaded. Now, coming the reward. Reward is the difference between the cost of no offloading and the cost of offloading solutions produced by the meta learning policy. So, it represents the improvement made to the partial offloading solutions achieved by the meta learner agent. So, here it is expressed in this particular form, that reward function to maximize the reward. Here this becomes the reward of no offloading, that is 0 means no offloading, it will be done on that particular device. Otherwise, this is the location, that is the solution produced by the meta agent here in this case. So, the reward captures how much improvement can be made to the cost of offloading when compared to the no offloading scheme. It will have the positive terms if there exists a solution which are better than no offloading. So, let us see about the meta algorithm. Meta algorithm has the following phase. First is the task learning phase, trains on known environment to produce the parameter, let us say theta 1, theta 2 and theta 3. So, these parameters are obtained by DQN. So, this is an edge and this is the cloud. So, different edge and different cloud, that means let us say that here in this method the entire edge cloud system model has 3 different environments, and the parameters which is learned is, let us say theta 1, this environment is learned called theta 2 and this is environment which is called theta 3. So, the meta learning phase produces a meta parameter out of all 3 learned parameters by meta learning of a previously estimated parameters. So, these are all called learned parameters, and meta learning is meta training is generating out of them by meta training of a previously estimated parameter, that is theta 1, theta 2 and theta 3. Now, let us see that in the deployment phase an unseen environment occurs during the deployment here. So, what is the parameter of this particular theta that will produce the optimal offloading decision in the environment? So, here to understand this, deployment phase, we have to take the samples from an unseen environment to train the model and find the optimal parameters. So, here you can see that, so it is already being trained and available, and a new deployment when it comes, now it has to now fastly converge to one of them depending upon depending upon the optimal parameters, that is theta k, using the meta learning. So, intuition is that the required parameter, that is theta k, are to be very close to the meta parameter, that is theta meta, since we have already meta trained the wide range on possible environment and assume that the new or possibly unseen environment lies somewhere in the same known distribution of the environment. This cause the faster convergence than randomly initializing this particular DQN. So, therefore, whatever parameters we have learned, this is going to be used in learning about the new particular parameter or new situation or new environment, and this particular meta parameter will be used to train quickly the new models or uninitialized DQN. So, conclusion in this lecture, we have discussed the deep meta learning methods, and that is the basic building block how the dynamic situations can be handled in the environment of the task offloading methods, that is in the edge cloud environment if it becomes quite dynamic. So, how are we going to use this particular quickly the train in the new particular situation. So, deep meta learning methods for task offloading model that helps to overcome the problem of poor neural network portability and in case of dynamically changing MEC environments. So, we have discussed the first order meta learning algorithm used to initialize the parameters of DQN in such a way, so that they can quickly adapt to the changed environment, and we have discussed this particular application of meta learning in the task offloading of edge cloud system. I hope that this meta learning has the great scope, and we have published our paper using meta learning for task offloading in edge cloud system, published recently in the transaction of mobile computing. I think if you want to read further, you can refer to our recently published paper on the same topic. Thank you.